Hey guys, this is Jack. I'm going to give you guys a quick, or maybe not so quick, but we're going to walk through very quickly what exactly we did yesterday. And then I'm going to go through how you might go through this data on Excel and kind of give you a little bit of guidance. I can't do everything for you, obviously, but I want to give you guys as much help as I can. And this is probably the most efficient way of doing it. So I'm going to go ahead and share my screen here, and then we'll get started. Um, okay, sick. All right, cool. So first of all, I'm going to pull up this. I'm going to be working completely out of this single data set that I sent you guys. This is just a combination of data I got from people that look the best. And that is going to be the easiest to work with because you're not going to really have to consider why you screwed up. Anyways, so let's talk about very briefly what we did. We did absorbance spectrophotometry. What that means is we're looking at the absorbance of light at different wavelengths of the sample, absorbance by the sample. And so you can imagine you have your sample right here. My head is the sample. You have light come in and you have light come out. The difference in the light that came in versus what hits the detector at the end is your absorbance. Now, how do molecules actually absorb light? Well, a very simple explanation is that when a electron is given energy, the right amount of energy, because to get from the ground state to the excited state, just to use a little bit of terminology, it requires a very specific quantity of energy. But when that specific quantity of energy is provided, then you can excite an electron. And so we're doing that with a photon. We're using photons to excite electrons. And if the photon is the right energy or the right wavelength, remember wavelength and energy are proportional, then that photon won't just pass through the sample. It'll instead hit an electron, excite the electron will go up in energy. A lot of other stuff can happen with the electron after that, but we're not concerned with that right now. So that's how absorbance works. It is the absorbance of photons of specific wavelengths by electrons. And you'll notice that you may absorb more strongly in some regions than others, like with proteins at 280. 280 nanometers is the wavelength at which proteins, specifically the aromatic amino acids, phenylalanine, tyrosine, and tryptophan, are going to absorb most strongly. And so in practice, we take advantage of this by looking at the absorbance at 280 to quantify proteins. And we'll talk about that more later. But just to kind of bring it back, we're looking at how much light was absorbed. Photons, light, wavelengths, all the same stuff. We're looking at where that absorption is happening for 4 different samples. So we're talking about lysozyme, that's the first one we worked on. Then we're talking about hemoglobin. Then we're talking about bovine serum albumin. And then we're also looking at DNA. Now, lysozyme is an enzyme that is involved in digestion, in cellular waste and things like that. And it's a run-of-the-mill protein. It doesn't really have any special cofactors or anything. So we're just looking at absorbance at 280 nanometers. And so you can see that these are in decreasing concentration. That's what we did in the lab. We did a serial dilution. And you can see that as we decrease the concentration of that protein, so too does the absorbance at 280 decrease. And this makes sense because we'd expect that if there's less stuff there, then there'll be less absorbance. And if we know that stuff absorbs more strongly at 280, we can look at 280 to look at that decrease in absorbance. Hemoglobin is a protein, not an enzyme, protein, but it does still contain aromatic amino acids. And so we do see a little bit of absorbance there at 280 nanometers, but we mainly see this huge peak at around 400 nanometers. That is due to heme. What is heme? Oh. Anyways, this is heme. So not going to get super into it, but things that have double bonds, these carbon-carbon double bonds, these double bonds are really good at accepting electrons because they don't even worry about it. They're just good at accepting electrons. If you want to talk more about that, we can. What they are. And so this is heme. This is a cofactor, so not part of the protein, but it associates with the protein. That goes into hemoglobin. see if we can get a nice little structure there of where the heme sits in there. You know, you can take from this what you will, but that heme gets bound into the hemoglobin, and it essentially acts to help the protein do its job, which is carrying, binding and transporting oxygen. Anyways, that heme, this is a huge conjugated molecule. This porphyrin ring, sorry, that is chelating the heme, and so, or the iron, and so we can see the absorbance of that really very pronounced at around 400 nanometers. That's because heme's extended conjugation. And again, as we dilute that away, we see that. This is the third sample, which is bovine serum albumin. It's just again, a very standard run-of-the-mill protein. It's used for a lot of things. It's used in the Bradford assay that we'll talk about in just a little bit. But again, we see the dropping down of that absorbance at 280. This kind of crappy noise here at the lower wavelengths is a result of those UV plates not being fully UV transparent. But you can still see that 280 is more or less the lambda max for the sample. Lambda max just means the wavelength at which maximum absorption occurs. And then lastly, the DNA sample. DNA absorbs most strongly at 260 nanometers. And indeed, in biochemistry, we can take advantage of this for, in the case of purifying proteins, which is something I do all the time, we can look at how much DNA versus how much protein is in the sample by looking at the ratio of the absorbance value we get at 260 nanometers versus what we get at 280 nanometers. And that's kind of all you need to know about that. But you can see here that, again, this is kind of a crappy plate, but there's a good amount of absorbance at 260 nanometers. If this plate was truly UV transparent, you would see something more like that, where it'd be peaking at 260 nanometers. Anyways, so that is a little bit of the background of what we did in the first part. Now, what you're going to need to do, I don't know absolutely everything you're going to need to do in the lab report, but you're going to need to plot these absorbance spectra on top of each other. Now, if you were to plot everything, I don't know if this will work all in one go, if Excel will be smart enough to figure it out. I'll try really quick. And I'll explain what I'm doing with all these steps in Excel as I go along. If you were to try and plot everything, it's a nightmare. You know, you can kind of see what's going on, but it's surprised my computer didn't crash. It's a huge data set. So I only want to look at the four, I want to look at one sample, one spectrum for each sample, or for each experiment, whatever. And because I want to be able to see what's absorbing the most, I want to look at just the top sample, the one that's absorbing the most. And that's going to be the first one in the series. So A1, A7, B1, B7. That doesn't make sense. Just kind of go through it and look, this is the top absorber. So what I'm going to do is I want to now plot, I want to make a graph that has those four lines in it. So the graph is going to have wavelength as the x-axis and the absorbance as the y-axis, just as these do. All I'm doing is I'm just taking this line, this red line, this red line, this red line, this red line, and I want to put them all on one graph. So what I'm going to do in Excel, I'm going to go here to insert. I'm going to go over to right here. If yours looks a little different, just find something that'll let you insert a scatter plot. And I want to use the one that has the dots with connected lines because I just want this to look a little bit more filled in. Make sure you have the dots in there, and hold on, it's being dumb. I need to make sure I don't have anything selected. All right, let me try that one more time. Okay, I'm gonna have to. Yours won't look like this. My Excel is just being very silly. So I need to just get rid of all of these. Hopefully, I don't have to do this like 100 times. Oh my God. No, come on. I'm just going to pause this recording. If I can figure out how to do that. Stop sharing. Okay. Yeah. Give me a second. So, okay. Cool. I hope I fixed it. Anyways, so I just opened this back up. I think I got confused because I was working on this document with another student earlier. So again, I just want to get a graph that has these four top lines. So I'm going to go insert. scatter here. Hey, I'm going to, it's still doing, are you kidding me, man? All right, sorry. Okay, third time's the charm. Anyways, so this is working now. All right, so got my little chart here. All I did was I went to insert, scatter, and I selected this one. Okay. Now all I'm going to do is right click on it, select data. So that brings me to this screen. Don't really worry about this chart data range thing. It doesn't really matter what we need to do. I'm going to add a series. Series is just a line. So I'm adding a series here, and I'm going to call it lysozyme because that's my first thing. It's the first protein. So I just clicked select. Let me just go back here. I'm going too fast. So again, add new series, lysozyme. Now I'm going to select my X values. You click this button here to select by dragging and pulling on the actual sheet to tell it what you want to select. So I'm going to select all of these wavelengths here. So the wavelength is my X-axis. It's going to be the X-axis for all of them. Now my Y values, and remember I wanted the top line from the lysozyme one, and that's going to be whatever was an A1. So I'm going to go over here. And I'm sorry, I can't zoom in. It's being dumb, but I know that this one's A1. So I do that. And if I want it to be done here, I hit OK. So I'm just going to show you what it looks like. And it gives me a graph. It's stupid and it made it the title, but whatever. We'll fix that later. Now, great. I just need to do the same thing 3 more times with the rest of these. So remember, this top performer was A7. This one was B1. And this is B7. So I'm going to be using those. I'm going to do it one more time. You're going to do the other two. But I'm going to go here, select data. I'm going to hit this button to add a new series. And I'm going to call this one hemoglobin. X values are going to be the same, just these wavelengths. Okay. Y values are going to be whatever was an A7. So come here, drag it down, A7. Okay. And hit OK. And would you look at that? Now I want to clean this up. I'll just go through how I would clean this up. So first of all, if you double click the chart, it'll automatically go over to this chart design tab. Alternatively, you can click on this and you can navigate your way over here to chart design. And then I don't want to have all this dead space here. I don't want to have all this dead space here. I need to label my axes and I need to title. So I'm going to go here to add chart element. First, I'm going to add my axis titles, primary horizontal, primary vertical, and I'll change those in a second. And I also want to have a legend so I know what's what. I think you should put it in the bottom. You can do whatever you want. So now I can see that the blue line is lysozyme, the orange line is hemoglobin. This is going to be wavelength. And of course, the unit is nanometers. This is going to be absorbance. And there's no units here because remember, absorbance is just dimensionless relative quantity. Okay, now how am I going to get rid of all this dead space, this nonsense space? So I'm going to just click the axis here. I need to move my little man. And whatever you click on while you have this pane open, if the pane isn't open, you can just double click something and it will open. So what I'm going to do is I'm going to click the axis right here, and I'm going to go to this thing. This is just like style, size, resize, and this is the actual numbers. So I'm going to go here to axis options, and the bounds are what I'm going to change. You're going to have to change this for the x-axis and for the y-axis. So really, I want this to start maybe right about 200, maybe 220. So I'm going to say 220, and then for the lower bounds, I'm not super concerned about this, but let's just keep it at 600. Okay. So all I'm going to do is hit enter, and look at that. Already, that's so much more useful. Also, I'm realizing that I forgot to add a title. Yeah, the way little man. Okay, there you go. There's the chart title. And you can think of something clever to call this. Please do. Don't have chart title there. Anyways, so I want to also kind of fix up this just so these can be more pronounced. I'm not really that concerned about this noise in here. So I might just do the same thing here. Click the axis options. For the minimum, for the maximum, I want to change the maximum because I really want to just look. I want this to be like my highest peak because this will be my highest peak. And so I'm going to say maximum 0.5. And look at that. Now I can see that absorbance at 280 a lot more clearly. Okay. So this is how you clean up your chart. This should be sufficient. In addition to having, a brief description above the chart. I think that's what your protocol tells you to do, or your the little resources you have on Canvas. Consult those, do what the course tells you to do. And you're just going to finish adding in the rest of those data series by going to select data, adding new series, doing the next protein, net next, and so on and so forth. You're going to do that the remainder of the 2 times to get the chart that has all 4 of your spectra stacked together. Now that's great. That concludes at least what's in the experimental protocol for part 1 of what you need to do. You might need to do some more with this data. And you have this raw data for everything. So if you needed to, for example, quantify the protein, you would look at 280. So this is an A1. This is for lysozyme. I could use this absorbance value at 280, as well as the extinction coefficient for lysozyme, but just go. And wow, look at that. You could use that to figure out the concentration if you so chose. Okay. I'm going to grab a drink of water and then I'm going to get back to part 2. Okay, part 2. All right. So remember, refresher, we did absorbance spectrophotometry here to look at where those different things were absorbing. Okay. So for part 2, we are going to build a standard curve with this first part with the Bradford assay. And then for the second part of part 2, these representing rows let's just say columns 9 through 12. That's something else we'll talk about in just a little bit. I'm just going to separate this for now, so it's a little bit less confusing. So this is the raw data I got from one of you. I went ahead and just put it in this more digestible format. And so what this is a standard curve. Now, what is a standard curve? You actually have already made a standard curve in this lab. All a standard curve is I want to figure out the relationship between how much of the stuff I have, i.e. the concentration, and the solution that I'm measuring, I misspoke. I want to figure out the relationship between the absorbance that I get when I shine light of a certain wavelength on this thing, and how much stuff is there, the concentration. So what you did in the first lab, depending on whether you use the right dye or not, my first section, sorry, I screwed up and you didn't get to use the dye, but still get data, is you built a standard curve. You added successively more dye. You looked at the change in absorbance. You made a line, and that line told you the relationship between how much stuff is there and how much you're absorbing. Now, the slope of that line is your extinction coefficient. All the extinction coefficient is the scaling factor between concentration and absorbance. It just relates the two. It's the slope, okay? So don't be too freaked out by extinction coefficients. It's just a slope. Okay. So what you need to do is you need to plot now these absorbance data with the units of absorbance on your y-axis and the concentration of your protein standard, which was bovine serum albumin, BSA, as the x-axis. Okay, so you might say, all right, cool, let's just go ahead and plot this up. Wait a second, you don't have, just from this raw data, you don't have the actual amount, the concentration of BSA. You're gonna have to figure that out. Now, depending on how you do the lab, some people made a little oopsie poopsie. It's fine, still, hopefully you made note of it. You were supposed to have a stock of BSA that was 0.05 mg per ml. And if you used the wrong stock, which was the stock from part 1 of the experiment, then you are at 0.1 mg per ml. It's just diluted by half. But I'm going to use the correct value here. And so this is great. We have the initial concentration of the thing that we started from. Remember, all we did was a dilution. We went from a stock into something else, right? That's a dilution. And so we have the M1 concentration of the stock. We have the V2, which is the volume to which we're making all of these samples, which is 200 microliters. And then we have, let's see here. Sorry, M1, M2, B2. Yeah, so basically, we're also given the V1. Now, where are we given the V1? Ooh, sorry. Here we go. Right here. So remember how it told you the volumes to use of each of those? That's just V1. V1 is the amount you're taking out of your stock and putting into something else. So these are your V1s right here. So well, this is for the rows 9 through 12. Your V1 is just this for all of these other ones when you're making your standard curve. So 0, 5, 10, 20, and so on. So I've already filled that out here for you. How nice of you. All you have to do now is just rearrange the equation to solve for M2, which is the effective concentration of that standard that's in the well. If that doesn't make sense, write out M1 times V1 equals M2 times V2, write what each variable is, and then you should be able to come to the conclusion that I need to solve for M2 because that's the concentration of bovine serum albumin that's in each of those wells. And that's going to be your x-axis. So working with equations in Excel, every equation starts with an equal sign. Okay, that's how you tell Excel, I want you to do math. Okay, so remember, if I want to rearrange this equation to solve for M2, what am I going to do? Pretty straightforward. I'm just going to divide by V2 over here. So that means, okay, makes sense. So I'm going to tell Excel to calculate that. Now, all I have to do is just select the right values and go for it. So first of all, what you can do, something that's really cool with Excel is you can type in an equation and reference some cells, and then you can pull that equation down, and it'll do the same equation as far as you go down. The thing is, unless you tell Excel to, it will, all of the cells you reference, it'll move them down at the same time. So you need to tell Excel to hold certain cells, like these values here. So I'm going to say equals M1 times V1 divided by, V2. But M1 and V2 are not changing for any of these. The only thing that's changing is V1. What I'm going to do is I'm on a Mac. There's a different shortcut for Windows that I'm not super sure what it is. But for Mac, all I have to do is say Control T. And that tells it to hold this cell, hold this reference cell. So I'm going to hold the reference cell here for M1. And I'm going to hold the reference cell there for V2. And what do you know? It's 0. That makes sense. But I can either hold this down or double click it, and it'll do all of that for me. So that's super easy. Now, what if you can't figure out this whole holding and reference cell thing, and this is making my life hard? I just want it to be easier. Sure. You can just say equals, you can just put in the value, not even reference the cell at all. Equals 0.05, which is M1 times V1 divided by N. If you haven't noticed yet, the equation that I'm typing out comes up over here. And then divide that by V2, which is 200. And you'll get the exact same numbers, right? The only reason that I'm using this format is so if, say at the end of this, my numbers look kind of screwed up and like, what happened? Well, maybe I wanted to see if, oh, maybe I did use the right one. Sorry. And then you can see like, oh, okay, well, that makes sense. Anyways, I can change this to whatever. And this can be really useful when you're using Excel for other things. But let's just stick with what it's supposed to be. Okay, this is great. Now I have my actual concentration of BSA, my protein standard. I should note the units here. So this is a mix per mil. And I have all of these absorbances. Now, I kind of just, basically, I could plot this right now, but there's something you should notice, and that's that the absorbance here, when there's supposed to be nothing in there, it's pretty high. Now, this is because the protocols that you guys were given and the ones that were loaded into the machines didn't account for a blank. And so we're going to need to manually blank our samples. So this is all uncorrected so far. So I'm going to get rid of all this. You can read this on the actual document. So what I'm going to do is, let's just say here, we hit merge and send it to make all these cells one. And say uncorrected. Now I want to see everything's the same. All I did was just copy and paste there. I want this to be corrected. I want to get rid of this absorbance line, because what's going to happen is if you plot all of this, you're going to get a line that, this is your origin, this is 0, 0, your x-axis, your y-axis. You're going to get a line that's up here because you're going to have some value that's your y-intercept, right? And what that's going to do is when it actually comes time to use this calculation for what we're going to use it for, is you're going to get a negative number and it's not going to make any sense. So we need to correct the data. So what I'm going to do is I'm going to tell Excel, all right, this blank is 0, and whatever this is, A2, I want to say it's whatever the uncorrected value is minus whatever my blank is, because essentially these zeros here are your blank, but you just need to tell Excel. And I'm going to do hold cell here with Control T. Remember, if you can't figure out or don't want to do that, you can just say minus 0.804. It's fine. But I'm going to be go. So now all I have to do is hold this down. And there you go. There are my corrected values. Now I should be able to just, if you just copy and paste that equation, it won't copy and paste the values. It'll copy and paste that equation. So it'll just do everything for you. So again, all I did, I set everything up here, set all my equations up here, Control C, Control V, Control V. And that will just copy and paste the equation. See how the equation is there instead of just a number, whereas up here it's just a number. It's because it did math on it. So great. Now this stuff is all ready to go to make my standard curve. I'm just going to go to insert. I'm going to do scatter plot. I don't want the line connecting everything because I'm going to make my own line. And so I'm going to select my data. So start a new series, just as we did with the last graph. I'm going to call this one concentration of BSA. For now, my X value is again going to be that concentration that we calculated about. And remember, look, it's the exact same as what it does up there. Okay. And then the Y values, I want all of these to be part, because we did this experiment in triplet, right? So we have 3 data sets. We have 3 data points for each concentration, right? So we have 3 total data sets here. I want each point to be grouped into the same data set so that when Excel calculates the trend line, it calculates it for the average of those 3 points. If you just have, if you were to just have 3 separate data series, it would calculate 3 separate trend lines, which I don't want. So I'm just going to do what you could drag this and then do a comma and then drag that and do a comma. I'm going to just drag this down, and then I'm going to hold Command on Mac or Control on Windows, and that will allow me to just keep selecting things as long as I have Control held down. Now I've got those 3 selected. I'm just going to hit OK. And what do you know? There's my standard curve. And this is all fine and dandy and great and grandiose. Just make sure everything's okay. Yeah, this is just covering that. Okay, great. So I would need to clean this up in the same way that I did everything else. And so I guess I kind of glossed over the theory here for Bradford assay, but it's all in your packet. You can do some digging to find out how it works. Anyways, so what we're going to do now is add a trend line. Okay, great. And so I'm going to go over here. I'm going to double click this, go over here to the numbers section. I want to display the equation. I want to display the R squared. And so R squared is just a statistical measure. You want your R squared ideally for something to be within a 5% or 95% confidence interval. You want your R squared to be 95 or greater, but realistically, you want your R squared to be as high as possible. R squared of 0.86 is pretty crappy, but oh well. Now this is great, but again, I have this intercept here, which is gonna come back to bite me in the butt. And I want this, I want my sorry, my AirPods just died. Bluetooth is off. Okay. Hopefully you can still hear me. I'm just gonna check my mic and make sure it's still working. So give me just 1 second. Okay, still working. So where were we? Coming back here. I want this to go through 0 because I don't want to have to deal with that intercept. It's going to make my life hard. And I want the model to account for these zeros here. So I'm just going to say set intercept to 0. And it'll automatically set it to 0. But look at that. It actually increased my R squared. So great. This is my standard curve. This is my relationship between the amount of stuff and concentration. Just to be thorough, I'll add the axis titles. Okay, so great. Now I have a working relationship between the amount of protein that's there, because a big part of the Bradford assay is that you assume that that dye complexes with protein, with all proteins the same. And so we now have this relationship for amount of protein there. You can just say standard, or you could even just say protein. And the absorbance. So what the second part of this second part is asking in columns 9 through 12, it's asking for you to now take this absorbance value and tell me what was the concentration of the stock we started from. And so you're going to need to figure out how to do that. I don't want to show you absolutely everything, but what you're going to do is I'm going to work one example for you. And I'm not going to use a table or anything, but that would be the more efficient way of doing this. So what you're going to do is, first of all, I've got this right here. This is my extinction coefficient, by the way, this 53.5, because that's just the thing that relates amount of stuff to absorbance. And what you're going to do is say, all right, cool. I've got these absorbance values. Cool. I'm going to say this is, first of all, this is my Y value, but these are not corrected yet. So I need to correct these. Did I fix that? No, it should be corrected. Sorry. Anyways, I'll just copy this. And so I'm just going to say equals this minus, and I'm not even going to do the whole hold cell thing. I'm just going to say, all right, my blank up here for this one was minus 0.804. And I'm just going to drag that down. Great. And then I'm going to do the same thing. Equals this minus 0.761. Great. The disadvantage of typing the numbers out like this is you can't copy and paste the formula, so it won't work. So whatever. So it's this minus, and the blank over here was 0.796. That looks a little weird. Maybe not. These data points just look pretty far off, but they come back together. So awesome. Now, yeah, okay. So this is supposed to increase, and indeed it does increase. These are supposed to increase, and indeed they do increase. Great. So what I can do is I could either do this calculation for all three of these. I don't know what your protocol tells you to do. Do whatever is on Canvas. But what I'm going to do is I'm going to average these out. So I'm going to say, and I'm going to say equals this. Well, let me start with my parentheses. There's this plus this plus this divided by 3. Okay. And I don't need all of those sig figs. Good God. Okay. So that's my average absorbance. And that's corrected. So now all I have to do is, this is my Y value. I need to solve for X because the reason we do the standard curve is I can now say like, all right, cool. Here's the sample of unknown concentration. It absorbs at 0.6, or it's 0.6, so it's going to really be down here. And so all you're going to do is just say, you're going to solve this equation here for x. You're just going to say, well, y divided by whatever your slope was. So 53.521. And wow, look at that. That's the concentration of whatever that sample was, whatever that well was, in mix per mil. We're not done yet. Remember, this is the concentration after you did a dilution. I want to know what was the concentration of A in the first place. And so to do that, you're going to need to back calculate, again, using M1 V1 equals M2 V2. But now you're solving for M1. And this just kind of illustrates how useful this equation is. So all I need to do is take advantage of the fact that I know V1, that's given to me right here. I know M2, that's what we just found out. And I know V2 is 200 microliters. So I'm just going to say that the calculated concentration of A, is equal to, parentheses, remember, solving for M1. So M2, which is this, times V2, which is 200, divided by V1, which is 10. And what do you know? It's not too far off from the actual value, which I believe is 0.3. I'll include that in the email that I sent out to you guys. But let's see what happens now if I, it might not work super well because I didn't do everything the most perfect way. Yeah, whatever. Anyways, this is relatively close to the value that should be 0.03. Pretty sure it should be 0.03 makes per mil. And we can do a percent error calculation, which is just the absolute value of the observed minus the expected. I need to do another set of parentheses here, divided again by the expected or theoretical. And so that's times 100. So 1.94% error. Go figure. Okay. So that's how you do everything. Hopefully this helps. Hopefully this answers your questions. If not, just reach out. But yeah, cool. I guess that's it. So thanks. Good luck.